Just a couple announcements. We'll have a review session tonight. Homework is due on Friday. Some problems from chapter 7, so we can discuss those or anything you want tonight. 5:30 in this room, and then we have a midterm in a week. So not today, but a week from today. That'll be in class. We'll do yes, no, maybe briefly on Monday, but we'll probably be going through invariance of the likelihood, invariance of the maximum likelihood estimators. We'll be talking about that probably next time, and we'll see how far I can get in motivating comparing estimators to each other. But essentially, you're just kind of looking at how much bias there is, how much variability there is in the estimator, and doing a comparison. And the homework actually works through problems like that. I'll probably ask you some problems like that. Okay. Let's come back to mixture models and where we were last time. So we have a specific problem that we're looking at. This is the additive mixture model where all the mixture components are Gaussian. Wildly useful models. So you can do a lot of stuff with these. This is all very extendable to, well, I would say all kinds of different stuff. You can almost approximate any sort of function with Gaussian. So if you have a smooth function or a smooth distribution or something like that, and you don't want to explicitly say parametrically what it is, maybe you can take this sort of semi-parametric approach. So semi-parametric meaning there are parameters in the model, but they might not have the typical determinations. So, but we'll study this in this context of just a K-component mixture model. I'll be having you do this in high D. So these will be replaced with inner products up here. So vectors multiplying in a matrix, multiplying in the vectors. I'll work out the details for you for this model, and you'll just extend to the higher dimensional stuff. So just as a reminder, the sampling process for sampling from this is first get your label. So these are your labels. This is what you're not going to observe, but you need those to identify the component that you're going to sample from. So these K's right here are the ZIs that you're plugging in, and they identify which one of those you have. So very often I'll write in to the notation ZI is equal to K, and I might drop that right in here. ZI is equal to K, just as a placeholder that there is a random variable in there that's identifying the parameters for sampling this other random variable. So there's two random components to the process. Just as a reminder, the EM algorithm is just these two steps right here. If you can write down the Q function explicitly, what you're going to do is you're just going to be running this thing in a for loop. For t goes from 1 to cap t, where this is something big. You're going to run it until this estimate converges. So you're just going to iteratively maximize this thing over and over and over again. If you can't write down Q explicitly, you might need to estimate it, and you would drop that into the for loop. If you have a Monte Carlo approximation, the expectation or something like that. For this problem, we're going to be able to write this down explicitly, and then we're just going to be doing this. So the problem that we're going to be studying is highly multimodal, and you would need a PhD to just even put a ding into optimization theory for optimizing any class of functions where there's lots of local optima. So people do this for a living, and they get into certain classes of problems. So what I'm going to say is what we're going to do for solving this problem is we're going to take all of our partial derivatives, set them equal to 0, and then solve for those. That does not give you a global maxima, but it'll give you local maxima. So we'll be doing that. How are we going to get at the global maxima? We'll probably need to start this process. It's an iterative process at different starting values and running it over and over and over again, and then collecting out of the local optima, figuring out which one is induces the biggest thing. We could consider that a global optima. How do you guarantee in any arbitrary problem you have maximized the problem? There's no such thing as a guarantee. You will never know for sure for any arbitrary problem. So how do you know you found the top of the hill if you can't see everything all the time? You don't really know. So for some problems, if you knew that things were convex, then you could say your local optima is your local optima. So people like about convex optimization. So if you hear somebody say, I work on convex optimization, what they just said is, I do the kindergarten version of it. I do the easy problems. I understand that there are some complicated problems in convex optimization, but the non-convex stuff is the hard stuff. So we're not going to guarantee that we're actually giving a maximum right here. But if you remember in our proof, we didn't need a max per se, we just needed to increase the function. So here's an algorithm for always getting to the top of a local hill. Keep making progress, and eventually you'll reach the top. It doesn't matter how you make progress, just as long as you have enough time to take that many steps, you'll reach the top of the hill. That's a guarantee. So no proof required. So you're not going to minimize something by moving up constantly. Okay, if you want to know more about that, there's a department on campus that specializes in teaching all about optimization. So lots of good classes you can take on this. Okay, so for our problem, these thetas are our model parameters. Those are our mu's, our sigmas, and our pi's. So all of these parameters right here. Mu k, the sigma k's, and then the pi k's. So those are the things that we want to know. These right here are missing components that we're averaging over. Right here we don't get to see them, so what does EM do? It does this thing that I accused of being Bayesian. You're averaging over it, you've turned it into a random variable, you took the expectation over it. So you average that thing away. So these right here are the z's. And our data that we get to observe that we're going to condition on our x's. So these things right here. So we're going to work out this function explicitly. First thing we need to be able to recognize, and this is the thing that I hope that in some like small finite amount of time you're able to do this for any problem. If you see the process and you know what the sampling distribution is, you can write down a likelihood function. Give me the sampling mechanism, I can tell you what the likelihood function is. They're one-to-one with each other. So many to one if you include the normalizing constant. If we don't consider the normalizing constant, the likelihood function is unique. So you tell me the sampling distribution, and it's a reconceptualization that I just plug in the data and think about it as a function over the model parameters. So our model parameters are right here, and we're going to be provided this stuff right here. So I'm going to assume you get to see the xi's and the zi's, and later on we'll take the expectation over the zi's. So what we need first is this part of everything. So we're just going to write this down first. We'll take the log second, so let's just write down the likelihood function. So this is the driving force of all inferential methods that are sensible. Write down the likelihood function. So you don't write down the likelihood function and you don't use the constraints of the likelihood function. I'm going to think if you get good answers, it's because you got lucky. So saying that we don't have to quibble. If you come up with good answers and a good process, you get credit. Okay, so what is the likelihood for this? And you get to see these. Some people will call this the complete likelihood function, and in EM literature they'll call it the complete likelihood function because you get to observe this. I don't use that terminology myself. I call it the likelihood function. It still is just the likelihood function. So I don't distinguish that terminology. Some people will call the other thing after you average out the z's, maybe they'll call that the likelihood or the observable likelihood function or something like that. But how you get it, you have to write down the complete likelihood. So let's just call that the likelihood. So how do we do this? What is the likelihood function? Again, whoever answers this first correctly comes and takes the chalk out of my hand and writes it down correctly on the board. I'll give you 5% hit credit. Any takers? You've been waiting for this moment all your life. Why do is answer a question real quickly. I'll give you 10%. What a shame, because it's in the videos from last year. So if you watch those, all you have to do is just think about the process. Any takers? They want to do it. No? It's not worth it. Would money change things? I don't have much money these days. Let me write it down for you. Let me write down something incorrect that I see quite often. So very often people do this sort of thing. I move 1n. So that's our number of data points that we observe. And then I'm just going to write down this thing. Sum k goes from 1 to cap k. And I'll just plug all this stuff in. We already know we can get rid of those, the 2 pi's. So we don't need that for anything. So I'm just going to write this down. 1 over sigma k. I'll put the pi k up here. So that's this. Then I've got the sigma k. It's out here. E to the minus 1/2 xi minus mu k squared over sigma k squared. Is that right? Is that the likelihood? I just took my model and I threw it in there. I see this very often. So when people are daring enough and they come in, what's wrong with this? Think about this. If I get an xi and I plug it into this equation, I'm going to plug it into this whole sum. So that xi is going to appear cap k times this sum. And you know the xi only came from one of those components in the sum. And so we need to indicate that. So this is real easy. All I have to do now is just write down the model indicator that zi is equal to k. And that's it. So now only one of these components is turned on simultaneously. So I can use that zi to indicate which one of these components was responsible for the xi. That kind of makes sense? So there's only one term in here because of that indicator. And I'm able to figure out which associated mu and sigma goes with it because the z labels that. So all I'm doing right here is I'm just producting together a whole bunch of these things right here, but I'm indicating which one I'm producting together. So they don't have the same mu's, the same sigmas, or the same pi k's associated with it. They change depending on z's label. Does that make sense? That's the likelihood. So just think about the process, what you actually did to generate the xi in the first place. So that is what I would call the likelihood function. It's just that thing. It has all of the data built into it. I've used all of the z's. I've used all of the x's. So everything's good to go. I'm going to rewrite this just a little bit differently. So this looks like this. Product down in front is exactly the same thing. What I've written down here, I've written down in additive form. And I've written this down with the indicator in additive form. So the indicator is a 1 or a 0, and I'm adding things up, and I only add together the value that has the 1 in there. So the 0 doesn't contribute anything. So I'm going to rewrite this just a little bit. We'll worry about this in just a second and figure out where to put it. So I'm going to write this down like this. I'm going to do this in product form. K goes from 1 to cap k, right here. And I know how to tuck these things into the exponent. So I'm going to do that just real quickly. This is going to look like e to the minus 1/2 xi minus mu k squared over sigma k squared. And I'm going to tuck these things right up inside and have the exact same thing. Minus, I'll do the plus first, plus log pi k minus log sigma k. So I broke those up into 2 terms. This isn't quite right. We have to do something else to indicate which term in here is turned on. This right here is this. They're exactly the same thing. You can break that out into a product, use the definition of log, you know which log I just used. It's the natural log. It's the one that is the inverse of that. So I have this in product form. If I cut this indicator still right out in front, right here, as soon as I have one of these being a 0, they're all zeros. Everything's 0 because I'm producting everything together. So I know in this sum right here, I only have one positive term, one non-zero term. Instead of making this in the product form to turn it into an identity, to make it akin to a 0 in the additive form, I have to turn it into a 1 in the product form. So what's the identity in the additive form? It's 0. So, or it's, what do I add to something to keep it exactly the same? It's 0. What do I do something in multiplication, make it exactly the same? I multiply by 1. So I can do that up here in the exponent. And so what I'm going to do is just tuck in this into the exponent upstairs, right here. So when that's a 0, it turns all of this into a 0. E to the 0 is a 1. And so this isn't algebra that I'm following. I'm just trying to make these look exactly the same and operate exactly the same. So I didn't do anything funny. I didn't take a logarithm of this and tuck it up in the exponent, because that wouldn't make any sense. So I'm not just using some algebraic identity. I'm thinking about it for a second. What would make this exactly the same thing, but in product form? Why do I want it in product form? Because now I know what to do with these two things. I can shove them upstairs, and taking the logarithm is exceedingly easy when you write it out this way. So there's a little bit of work when you do the EM is figure out how do you write this thing out so that when you take the logarithm, everything is very easy to work with. So, but I like this. It makes things simple. Again, I didn't follow any algebraic rule to just take this thing and throw it up here. I just thought about what turned it into the multiplicative identity. Does that make sense? This is probably the hardest step for most people to see is when they look at this, they look at that. So if they're doing their third grade version of algebra, it's kind of hard to recognize, but if you just take a step back and think about what those two functions are and recognize them as exactly the same, I think you're on your way. So this is our complete likelihood function. So what I'm going to do next is I'm going to shove both these products up into here and then take the logarithm. Let's do that in one step.
Can I ask a question? Why is K becomes the production loss?
Because I made it that way. Think about this. How many terms are in here that look like e to the something? And not just a 1. There's only one of them. How many terms are in here that look like this thing, e to the something, that isn't a 0? It looks like that. There's only one of them. So I'm going to let you chew on that for a while, but this thing right here is identical to this. Just do it with an example and you can see it. I think what confuses people is they're trying to follow a third grade algebra rule or something like that. I don't know if that's when I learned algebra. I'm just scared to go that far. Anyway, just chew on it. Recognize them. They're exactly the same functions. I can change additive identities into multiplicative identities by throwing the indicator up into the exponent. It'll work every single time. So all of these mixture models, this is the trick. So if you're working in the exponential family, this is really easy to do. Did I at least answer the question or at least fumble around it for a while? Okay. Questions? It's that step for some reason. You know, I'm going to let you stare at it. It's in the video. So, okay. So here's log. Log, and I'm going to write it down using beta just to save myself some notation. Right here, I'll write down this is the z's. right here. So theta is just the mu's, the sigmas, and the pi's. Given my x's right here, expected value of this whole thing, right here where I take the expectation over the z's, given the theta t's. Actually, let's forget about this for a second. We'll come back to that. Let's do it in two different steps. So just log likelihood. So this thing is just going to be, I'm going to take these products, put it into a double sum into the exponent, take the logarithm, it'll get rid of the e. So this just looks like this. Sum, I goes from 1 to n, k goes from 1 to cap k. Minus 1/2 xi minus mu k squared over sigma k squared plus log pi k minus log sigma k times my indicator function. I want to remind us that we get to observe the data everywhere in all of this. So I'm always getting to see what the xi's are. So I get to see it in here even though I didn't really put it down, but I get to condition on all of my x's. That's always true. So I said that repeatedly when we went through our proof. We always get to observe the x's. You can condition on those everywhere. It's conditioned everywhere. So conditioning on this data right here, I can also condition on the data. Sometimes I forget to mention that, but if I don't look at the data and try to do something, I just made a mistake. There's probably information in there. So that's this right here. So there's my complete likelihood function. I've taken the logarithm of it, and so I have this part, and now all I have to do is take an expectation. We're taking an expectation over the latent stuff, so in our case, that's the z's. So I need to take an expectation over this. But this is all very convenient because this part has nothing to do with the z's. This is a constant with respect to the z's. And this is just a linear form, it's just an additive form. And so this is going to factorize outside of the expectation. And the only place I see the z's are here. So the expectation of the log likelihood and I'll remind us this is over the z's, and I'm going to condition on theta t. I'll say what this means in a second. So this is only going to affect the expectation of everything, but I get to know my model parameters at the previous step. Let's just remember what the thetas are to us. It's the mu's, the sigmas, and the pi's. So this is going to look like this. Double sum, 1 over I, 1 over k. I'll come back and I'll complete that in a second. Minus 1/2 xi minus mu k squared sigma k squared plus log pi k minus log sigma k. And now I have this expectation here. This is over the z's given theta t. Right here, this is going to be the zi is equal to k. Gross indicator. So the expectation slides over the top of that. There's no z's in there. The z's are just in these indicator terms. And so if I could come up and figure out what this thing is analytically, then I can start maximizing this. So let's think about what this means right here. So let me just ask the question first. What is the expectation of an indicator? So let me just reminder. expectation of an indicator function of an event, some event that happens, is equivalent to the probability of that event happening. Somebody explain that to me. It's like a Bernoulli. So Bernoulli, what's the expectation of a Bernoulli? It's the probability of that event. So this is a Bernoulli sort of thing. So probability of that event. So expectation in the z's right here, I can plug in all the z's right in here, cap z, but there's only one zi at a time. So there's a whole bunch of these right in here where they're getting indexed over. But for each one of these, I just need to consider the expectation over zi because there's only one of these that occurs in this indicator at a time. So the expectation of zi, given model parameters theta t, and I'm going to remind us we also get to see the x's. But let me just ask you a question, which x's are important for understanding that z? There's only one. There's only one of the x's that we can use to determine what its label is. All the other x's don't help us. They help us to identify model parameters, but they don't help us if I knew what the model parameters are. I.e., this says something about that. For a current step in the algorithm, then only one x is going to help us to understand what that zi is. So I'm going to condition just on the xi, which is our data. So indicator zi is equal to k. So this is going to be the probability that zi is equal to k. But I get to know some stuff. So I get to know what the xi is, the associated xi, the data. I could look over all the xi's. You can add them if you want. So you can look at other xi's, but it won't help you with anything. They're all conditionally independent of each other. Conditional on what? The model parameters. So these things. So I get to know those. So what does this notation mean? It means I get to know that stuff at this step when I compute this probability. So these are my mu's at time t, my sigma at time t, and my pi's at time t. So I get to know all of those. So again, this is an iterative algorithm and I need to start the algorithm somewhere. So at the first time step, those are whatever you've initialized everything to be. So your initial values. So how do I come up with this? So what we want is this probability of zi is given, zi is equal to k given the xi and given model parameters. So I get to know some values of mu, sigmas, and pi's to evaluate all of this. So if you're going to try to compute this probability, how do you do it? I'm just going to remind you, we don't know that off the top of our head. We probably need to say some stuff, but we do know this. F of xi given my model parameters. Mu, k, sigma k. And if you like, I can write in this zi is equal to k. And that might help you to think about what is the answer to this thing. I know this. We've been writing that down the whole time. I can do this for all the k's, so I've got all the model parameters in a particular time. I can throw labels on these, if you'd like, and say that I know them at some time in the algorithm. And I guess that's okay, I can write that stuff down. So how do I change this into that? There's only one gig in town. Bayes is down. That's why Bayesians look at this and they say it's Bayes. How do you move from this to that? And so it's a conditional flip. I want this to come over here, I want a conditional flip. So So I know how to do that. It's Bayes' theorem. And so Bayes says this. So probability of the Zi is equal to K, given all of my model parameters, and Xi is going to be equal to f of Xi, given all of my model parameters. I'm going to write it out as theta t. I get to know them for all of everything. But I can be a little bit superfluous and tell you more than just those and tell you all of them, if you'd like. Some of them are conditionally independent of other ones. I can just chuck those. So, but this has the information about these two. It also has the information about all the other ones. So this is going to be Zi is equal to K. So times the probability that Zi is equal to K divided by sum fxi given theta t, Zi is equal to K, probability Zi is equal to K. K goes from 1 to cap K. Let me just write this out even more explicitly so you understand what I've just written down. This is 1 over 2 pi. I'll write those in. You can get rid of those if you want. E to the minus 1/2 xi minus mu k squared over sigma k squared times the probability that Zi is equal to K divided by 1 over 2 pi square root sigma k. I've missed this one, sigma k. There's a sum out here. K goes from 1 to cap k. E to the minus 1/2 xi minus mu k squared over sigma k squared. Probability Zi is equal to K. That's Bayes' theorem. So I just take the density function and I plug it in. If you don't like that these are k's down here, you can switch everything in the denominator to j's. This is for a particular k right here, and down here I've used k as a dummy variable. I'll make it even more easier to j, make that one a j, that one a j, that one a j. So that's what it is. So let's imagine I had a mixture model. Let's say cap k was equal to 2. And I had current estimates for my mu. So this is going to be mu1 at some time period. Mu2 at some time period. I've got some sigmas in here. Sigma 2, sigma 1. And if I see an x in here, xi, I can measure using a formula like this to see which mode I think everything came from. So it's the same picture that I've drawn for you a couple times. And this is that associated probability. I should say something about which mu's are these, which sigma is all that. So those are the things I get to know in the previous step of the algorithm. So these are t's right here. T's on all these model parameters. So this is where you use the previous values in everything. So in the iterative algorithm, the previous draws go into this step to inform what the z's are. Then we're going to take those probabilities that we can compute, and we can compute one for every I goes from 1 to n, and then we can learn the model parameters. And then I can go back and do this step. So what you're going to do is you're going to do this for all I and k. So I goes from 1 to n. This goes from 1 to cap k. So I can compute these model probabilities right here for every I and every k. And that's what you're going to do. I'm going to give this a name. I'm going to call this pi I k time t. So that right there is the probability xi came from component k. And this is utilizing the index in the algorithm. So that's what we do. So that's the one step that's missing from the homework assignment, is computing all of these probabilities. So you're going to update all of those probabilities. Now you know these things are probabilities, things add to 1, so you probably don't have to do this for all cap k components. You probably have to do it for cap k minus 1 components, because everything necessarily adds up to 1. How do I know that? This thing is normalized right here. This does bring up the question of, what do you pick for this? What is the prior on the z's? Now I see this as something that I like. This gives me a lever that I can pull, that I can push things in one direction or another. So let's imagine that my 2 components or something were maybe a spam filter. So going back to that example, I got spam or not spam. Something like that. I'm going to measure something about the emails, and I'm going to determine whether or not it's spam or not spam. So the question is how do I want to bias everything? In which direction? If I thought that it was equally likely a priori that I saw a spam versus a non-spam in my email account, I'd probably pick those to be a half and a half, uniform. So if I knew something about my empirical rates, maybe from the past, of how often I see a spam, then I might inflate that. So I might calibrate those priors to the group sizes that I anticipate seeing. And so if you ever see this stuff in MATLAB or R where you can sit there and add a probability for the group size, they're probably doing maze in the background. So some people don't even talk about this and they get rid of it. They just say, I'm not doing maze. I just took the likelihood function, I plugged everything into it. That's all I did. So a Bayesian would say you used a uniform prior, it just canceled out. So one judicious choice would pick this to be 1 over cap k. And if you picked it to be 1 over cap k, if you didn't have any information on the labels, these would just cancel out, and all you're left with is this part. A lot of people spend a lot of time coming up with names of things so they don't have to say Bayes. So in the ML community, some people will call this the responsibility index. For me, I like to call it the posterior probability of the label. So I like that terminology, but if somebody said I want to call it something else, that's fine. So there are other ways to deal with this. I could iterate over this and I could come up with an estimate of these probabilities and plug them in. That's a version of empirical Bayes, and we're not going to go into that. Some people will call it reinforcement learning. So again, there's a lot of different things you can do with this formula. I think for your assignment, we're going to assume this is a uniform prior. But there are other possibilities, other ways that I can turn that lever. If I didn't know anything, just uniform is fine. I will say if I do anything else, and I let these update iteratively, I violate the likelihood principle. Maybe you don't do that. So, okay. Let's go back to the Q function. Let's just remember this notation right here. Those are my model probabilities, and I'm just going to change out this expectation that we took everything over with those pi I k's. It's the expected value of those indicators. So let me just rewrite everything again. So Q, you can write down. So our Q function for this thing is going to be equal to double sum. I goes from 1 to n, k goes from 1 to cap k, minus 1/2 xi's minus mu k squared over sigma k squared plus log pi k minus log sigma k. And now I have some new notation for that expectation, pi I k. So what are these pi I k's? They're the expectations of the indicators. What are the expectations of the indicators? Their probabilities of group assignments. How do I compute those? I just go to this formula. So And I can always retrieve those in the previous iteration. So I'm going to write down a T on here just to denote that. So that has all my current model parameters in there. I use them for my last step to compute these probabilities. Now I can start taking derivatives over this function and start solving for the mu's. This pi. This is not this pi. This is often confusing. This is the total probability of being in the group. This probability is specific to us in xi. So these are the individual probabilities. Obviously, they have something to do with each other. Josiah?
I'm wondering why you might not use the pi k as required.
Yeah, and I answered the question. You could. So I could update those and I could throw them in there. So I could update these at time t and throw them over here. So I need to talk about a lot of stuff. And of course, I like to get philosophical, talk about likelihood principles, so we're not going to do it. I will say this. You will converge to a local faster if you do that. So it either diverges from the global fast and converges to a local very fast. So it could be a good thing. Could be bad. So you can experiment if you want to code it up that way and compare. It's not hard to do. Let's try to get some of these estimates right here. So that's my Q function. This theta, these thetas right here are these. These thetas right here, just for notation's sake, are all the model parameters that went into these right here. Those appear here in these probability updates. So they're different. So you want to keep track of those. So let's just do this. Let's say I want to find out an estimate for mu1 in all of this. I'll have this Q function, theta t. I'm going to take this derivative. Where does mu1 appear? It appears in this part of everything. So there's only one of those in here. And so this whole term will be 0 for all of them except for where I observe the mu1. And so I'm just going to take that derivative. These are all zeros right here. And I'm still going to have this thing multiplying into that right here. So this is going to look like this. Sum I goes from 1 to n minus 1/2 xi minus mu k squared. Take out the square, bring down the 2 right here. Divide by sigma k squared. These are all zeros in here, plus 0 if you'd like, times the pi I k. I can throw the time index on that. So that's all very nice. These two cancel each other. Negative sign doesn't really do a whole lot. For all of this, it's going to cancel as soon as I end up taking a derivative. I didn't take this negative sign. I should have done that. Chain rule right there. It's not really going to make a difference. I would have gotten lucky if I forgot to do that. So this is going to imply that sum of the xi's minus mu k, I'll throw a hat on there, over sigma k squared times pi I k, and time t is equal to 0. So I'm going to solve that. You'll notice this thing doesn't need to go there, and I'll let you do the solve. But here, everything is, this is I goes from 1 to n. When I took the derivative over mu1, all of the other terms in this sum disappeared. Because those are over mu2s, mu3s, mu4s. So this is easy to solve. I'll just write this down. Mu k hat is equal to this thing. Pi I k xi over sum of the pi I k. And I'm going to throw a label on this. So I've got my little t's. right here for those pi I k's. And I'm going to throw a label on this, and I'm going to call that t plus 1. So my next time step, when I come back here, after I solve for everything, I'm going to be using that. Oops, this is mu1. And I can do this for all k. So in general, we know what the things look like. So, oh, sorry, this is 1. This is 1. And my bad, right here, these are going to be 1s. I, 1. Oh, no. Let me redo that. This is going to be I, 1. I, 1. I think that's right. This was a sigma 1. Right in here, and this was a mu1. This right here was a mu1. This is a 1. That is a 1. In my head, I was doing this as though that was mu k, but I gave it a specific label. So that's 1. My k in that calculation is 1. It's not a hard derivative to take. We can come back next time, do one more of these. But I'm going to just tell you what they are. Actually, I think we have time right now to do one more. Let's do this over pi 1. So that's going to be this one, right here. Let me make this really easy. I'm going to say cap k is equal to 2, just so you can see everything in here. And I can write it out explicitly. So I got this term right here. I'm going to have cap k is equal to 2 right here, so there's going to be only 2 terms in the sum. I can forget about these right here because they don't have the pi k's in there. So as soon as I get them with a derivative, these terms right here, they're going to disappear. And all I'm going to have is those terms. And I'm going to have 2 of them. So my Q function looks like this in terms of the pi's. It's going to look like this. Sum I goes from 1 to n, pi I 1 looked at this formula. I know I'm going to solve everything for this right here. I know when I take a derivative, these 2 things are going to disappear. Cap k is equal to 2, and so there's only 2 components in this sum, and that stays the same right there. So this is all you're going to have. We need to be a little bit careful when we do this. We have a constraint, and our constraint says this. These are probabilities. So we need to incorporate that constraint. Let me just do that in one step. 1 minus pi 1. If you want to go through Lagrange multipliers, ultimately you do this. That's what Lagrange multipliers essentially does for you. It solves for the constraint. That's one of your equations. And you just plug that thing straight in. So what I'm going to do is I'm going to take derivatives. Pi 1 of this function, q, and this was going to look like this. Sum of the pi I 1s, 1 over pi 1, plus sum pi I 2, 1 minus pi 1, that goes on the bottom down here. Chain rule, turn that into a negative. Set that equal to 0 and solve for these. And you can throw some indices on here. So these are going to be my t's, right here from this calculation at the previous time step, and you're going to update those at the next time step. And you can solve that equation. Let me just write down what the solution is to that equation. You don't actually need these in any of the update steps for your homework assignment, but what you'll get for this is just these. Sum of the pi I1s divided by n. If you solve this for the pi, you'll come up with this. So this would be my total probability. What is it? It's just the average of all of those group probabilities for each individual. Kind of makes sense. So that's the MLE. This is the thing that Josiah was asking about, is why can't I use these as my prior in my labeling steps, where I come up with my group labels, the probabilities associated with those. You could, and people do it. So, I've got no problem if you use these as your Bayesian prior at every step. I don't love it, but I also know what happens. I don't love it because it violates the likelihood principle and it's hard to explain. Saying that, it converges faster, and I can explain that. So that's a good thing. Let's come back next time. We'll follow up. I'll write down what the estimates for sigma are. We'll talk about what you're supposed to implement, and then I'll show you my version of the code. I'll do a simplified version for you in one dimension, and I'll show you what you're supposed to get. And then we're going to move into invariance of the likelihood function and comparing estimators. That's it for now, you guys. Thanks so much. Next time. EM works. I'll demonstrate that to you. Let's begin. I just want to remind us where we were last time. So we were kind of looking at this function right here. And your job for your simulation assignment is to just parameterize this in high dimensions. So where you see this thing as a square, you're going to have an inner product between vectors. You might have a covariance matrix here. You can't divide by covariance matrices, so we throw it up with the exponent as an inverse function. So you'll reparameterize everything. And all the derivatives that I've taken, you'll be able to take as well. Like the first derivatives on everything on mu, it's just what you think it is, the first derivative. When you go to take the derivative over a matrix, you might want to be a little bit careful about that. So I'll let you kind of fumble through that a little bit, and hopefully you go to like a matrix cookbook and look up the derivatives. If you do have any questions about it, I would be here next week to help you answer those questions. But we can at least write down a formula and know what the answer is. So if you've never taken a derivative over a matrix, spend 10 minutes and try to figure out what that even means. What you're really doing is you're taking the derivative of all the elements of the matrix and setting them equal to 0 and doing a solve. Keep in mind that positive definite matrix or a symmetric matrix, you're only taking the derivative over the unique elements in that matrix. So the top triangle and the bottom triangle are the same. You're not taking derivatives over both of those elements, just one. So if the ij element is the ji element, you would denote that. We were here last time and we were taking some derivatives over this function. I'll just remind us what this function is. So this is the function that you're going to optimize, which is equivalent to optimizing the original problem. So we worked through this. I'll just point out these parameters right here, thetas, are these. Those things right here. The theta t's are the things that we're conditioning on when we evaluated these probabilities. So these right here are the probabilities of data point I coming from component K, where I've written those down right here. So I wrote in the prior is just a uniform prior, but there is some wiggle room with this. You can pick priors different ways. So different types of Bayesians differ in the types of priors they're using. Of course, if you didn't know, if you have no reason to believe that the groups were imbalanced or anything like that, and you didn't know anything about the groups, you'd probably just use a uniform prior. And a lot of people do this. And if you do that, this just cancels out right here. I'll say for your homework, that's the choice I would probably use. Some people don't like to say that they're Bayesians, even though they might use this exact calculation. And I guess that's more of in line with what were you thinking about when you came up with your estimators versus what is the performance of your estimator. If they're exactly the same thing, if I come up with this as a Bayesian or a non-Bayesian and I'm using it, I guess that's all I care about. That you're doing the right thing. So you have different reasons for thinking about it differently, I guess that's okay. So sometimes people will not call this the posterior probability prob of xi from, I'll call it component k. The way that I would write that out is the probability that xi, or I would say maybe zi, is equal to k given the xi. So this is the way that I kind of derived it, and I thought about it that way, and I also get the condition on all my old model probabilities. So this is what we derived from last time. If you don't like to think about it that way, you could come up with another name, the reliability index. Or sorry, I think this is called the responsibility index. I've heard people in the machine learning world do this. They do EM too. Everything we do probabilistically, they probably do as well. They have different names for it. This is a neat trick. So just come up with something that sounds cool. And so people let that slide instantly. So I kind of like that trick if you don't want to get into a philosophical conversation. I will mention I gave a conversation on Bayes yesterday. I gave a workshop over to a group of population ecologists. And basically their whole concern the whole time was, what is it with Bayesians always fighting with everybody? And it's like, well, it takes two. You know, so it's a cultural thing. So that we have camps and we like to fuss with each other. I would love if one of these days we can get past that. So who did that? That's Fisher and Dennis Lindley probably, you know, made us think about things this way. I kind of like, if you like thinking about it that way, that's cool. If you like doing something different, that's cool too. So lots of ways you can explain things. So this is our whole thing. We took some derivatives. We did one over mu, and we came up with an answer. You can redo that calculation. But we came up with mu hat for component k. This was just this. Pi I k's. These model probabilities times xi divided by these probabilities. So this is just a weighted average. I goes from 1 to n, I goes from 1 to n. So instead of putting a hat on everything, what we've done is we've just upgraded that to our updated parameter estimate. So that's what happens when you optimize over that mu right here, take a derivative over this mu, set everything equal to 0. You could probably check the endpoints, but you already know what this function looks like. It's a parabola. So you know that what a parabola looks like. There's a one maximum and it's not on the endpoints. How do I know that? I can picture it. I'm not sure how to explain that. So, but we're familiar with this function enough. So we probably don't need to check all the endpoints. I'll forgive you if you don't use something like that on the exam. As long as you say, I know this thing, it's going to have, it's just a context function. Okay, so that's what we did to derive that. I went through this really quickly last time, and somebody asked me a few questions about it, so I think it's worth going over again. For the pi's, pi k updates, I'll just redo what I tried to do last time on the board and not shortcut all the steps. For the pi k updates, I said let's just look at k, cap k is equal to 2, and everything generalizes. So we'll do what I call grad school induction. So do it for k is equal to 2 and just generalize. So I can usually do an induction proof in my head and see if it's going to generalize, so I don't know why I need to do the extra details. But when I was a math major in an undergrad, that would be the difference between an F and an A. So I would do all the details. I guess I'm okay in this class, since that's not exactly our goals. If you do induction proofs in your head and you say everything generalizes. Of course, if you're wrong, that's where you're going to get marked off. So you better be right. Okay, what we did is we just wrote down this Q function again. I goes from 1 to n, and I just expanded the inner sum. So let me just do that and write in all of my terms, because I got rid of all of the terms that didn't involve the pi's, because I knew when I took a derivative, they're all going to 0 anyway. I think that confused a few of you. So let me just go through this again. This would be mu1, right here, sigma 1 squared, plus log pi 1 minus log sigma 1. And I'm going to multiply all of these things. So this is a little bit untraditional notation. But these are all multiplied by pi I 1t. So those are the terms that are all getting multiplied by that. So multiply all of these terms by that, right there. So, and then I have this other term for the other component. These are the xi minus mu2s divided by sigma 2 squared plus log pi 2 minus log sigma 2. So just expanding this function. All of these terms are multiplied by these pi I 2's. So just these things. These responsibility indices. So those are all multiplied by those. Okay. So now I'm going to take a derivative over this thing with respect to that parameter. But I have to remember this parameter has something to do with that. So in fact, if you tell me what that is, I can tell you absolutely certain what that is, because cap k is equal to 2. So there's a constraint that all of the model probabilities add up to 1. So we also have the constraint pi 1 plus pi 2 is equal to 1. So this is essentially what Lagrange multipliers does, is they just replace that in there. In Lagrange multipliers, you always get the constraint right back. So I can pull that over to -1 right here, add that in as a constraint with my Lagrange multiplier, take a derivative with respect to the Lagrange multiplier, set it equal to 0, and you get the constraint back every single time. That's what Lagrange multipliers does. It just adds that constraint back to your equation set that you need to solve, and then eventually you plug it in. So I'll just do it in step 0 and just throw that thing right in there. And then I'll take a derivative with respect to pi 1 here. Okay, so let's just do it. So I'm going to say this is Q star. And that just, the star just denotes that this is the special case for k is equal to 2. So derivative with respect to pi 1 of Q star. If I take I'm going to roll this thing over the sum. Pi goes from 1 to n. When I take the derivative over this, it's 0. So there's no pi's there. 0. That's what I shortcutted in the first place. I never wrote it down because I knew I was going to take the derivative over it and it'd be 0. I tried to explain that in 2 seconds. So this is what I really did. I just removed this because I knew as soon as I took the derivative, it's going to 0 anyway. So now I take the derivative over that one. I can multiply this by this thing right here that doesn't have the mu's in there. The mu's that are in here are a different set of mu's. and they're indexed by t. So while they might look similar and they have something to do with the other mu's, they are different. So I can multiply this 0 by those, but it's still 0. So take the derivative of this term right here. That's easy enough. 1 over pi 1. And then I need to multiply by these weights. Pi I 1 t. So I'll include those. When I take the derivative here, it's 0. So this is minus 0. Right here, take the derivative here, it's 0. So plus 0. Derivative here, it's got a pi 1 there. So this is going to be 1 over 1 minus pi 1 is that derivative, and I need to be a little bit careful with the chain rule. So that's the chain rule derivative of minus pi. So we'll be careful there. Usually I circle these things when I get confused over the signs and I need to be aware of them. We would have noticed we made a mistake when we set everything equal to 0 and we're going to drive something negative. You could probably catch that real quickly. That's multiplied by pi I 2 in t, and then the derivative here is 0. So minus 0. So that's what we had last time. So this whole thing is just going to be sum. I'll write it like this, 1 over pi 1, pi I1, t, I goes from 1 to n, and this is going to be minus 1 over 1 minus pi 1, just factorizing those things out, sum, and I'll distribute my sum operator across the sum, so pi I2 times t. So that's what I end up with. So that's where we left off last time, the whole thing that I was scribbling down. Somebody asked me at the end of it, how did my pi I2s disappear from the answer? I'll show you in a second where they went. So what I'm going to do is I'm going to set this equal to 0. As soon as I do that, I don't have equality in everything, so usually I put an arrow over there. But this implies this. And very often I throw hats on things. I'll leave them as hats, but we know what the hat means. The hat means the same thing we did over here, where I'm going to index by t plus 1. I'll just leave them as hats and then change it at the end. Get rid of this. And so I can just rewrite everything. I'm going to pull this over to the right-hand side, and then I'm going to pull the pi 1s over to the left-hand side. Let me do that in one step. 1 minus pi 1 hat over pi 1 hat sum pi I1 t is equal to sum pi I2 t. So again, I pulled this over, and then I multiply both sides by that. Let me rewrite that. This is 1 over pi 1 hat minus 1. So I can pull the other thing over here. When I multiply this minus 1 by that, it's just this thing, so I can pull that over to the other side. So again, not equal. This means that 1 over pi 1 hat times this, pi I1 t, I goes from 1 to n, is equal to this thing plus this. I'm going to pull that one over. So sum of the pi I2s plus the pi I1s. I could have brought over a whole sum, but I can just use the same sum operator on both of them, since they're indexing over the same things. This goes from 1 to n, this goes from 1 to n. I just use that minus 1 to pull this one over, and then I distributed the sum across everything. This is 1 right here. So these model probabilities with the t's on them, they also sum up to 1. So and that was by design. Keep in mind what we did is we computed this thing. Again, you don't need any of these normalizing constants when you do it. That's why we're always writing down proportionality, because they always cancel. So, but this is necessarily something that lives between 0 and 1. These are all positive up here, and it's normalized. So we know that those add up to 1 as well. So that's what we do here. When I add them all together, I wind up with this whole thing, this whole sum right here is just n. So then I have these things over here, I can divide by them. And then I have the inverse of my estimator. And I just need to flip it all over. So I'm going to take some of these, take n divided by it, and then invert the whole thing. So what does that mean at the end of the day? It means this, pi. This is 1. Half is equal to sum of the pi I 1s times t divided by n. Pi goes from 1 to n. So that's just a little bit slower version on this. Now let's induct. So grad school induction. And I think I was mincing this and doing induction halfway through and throwing k's and 1s all over the place, so sorry for that. So that's true. There's my grad school version of induction. I did everything right for this. They're all the same by symmetry, so that's got to be true. So non-mathematicians and engineers, physicists and stuff say, what do I need a proof for? I guess I'm okay with that. So instead of the half right here, these are what we're using at the next iteration. You never actually are going to use these in your calculation. Josiah made a point that said, why can't I use those right here? And you can. So I will say this, if you do the full Bayesian thing, and you're trying to construct a posterior distribution on theta, which is a slightly different goal than what EM is accomplishing, it's just maximizing, you're going to mess up all your uncertainties in theta. So it'll reduce them if you plug this thing in. So EM is not accomplishing that goal, it's just maximizing something. And it turns out, if you do use this right here, it will converge to the same answer. And it will do it even faster. Saying that, there's local modes in everything, and so converging fast can make you converge to the wrong thing even quicker. So that could be an advantage, maybe, maybe not. I don't see any great reason for having to do that in this exercise, but you could incorporate that here. You could also let these be different depending on what you already knew. If you have prior information about the class probabilities, so you knew that group 1 only happened like 10% of the time, you just happen to know that, and group 2 happened 90% of the time, you could encode that. I don't see any good reason for doing that in your assignment either. You could use the truth. If you knew what the true probabilities are, you could just include it right in there and not do the updates. Lots of possibilities. You won't use those, I don't think, unless you happen to just start exploring other options, but you will be using these in the algorithm. You'll need those for computing every day. So, but if you wanted to estimate those and report these back, these are what you would report at the end of the day once they converge. And it kind of just makes sense. It's the average. What else would it be? I say that after we derive it. I go, okay, that makes sense. Because you never know. This is the weighted average. So it's just weights with respect to those inclusion probabilities or responsibility indices. I haven't derived this, but we can also update the sigma k's. I'm going to write this down squared at time t. This is an excruciatingly painful notation because I have the index in both places, but I think you get what I mean. Very often I'll end up changing that to a v so that I don't have this problem, but I'll make a point using this notation in just a second. But you get it. It's going to be the update for this variance parameter. This thing is going to look like this. Sum pi I k's. So these same model responsibility indices times xi minus mu k at our previous location. You'd probably use this one right here. So this is going to be t plus 1. So when you're solving this joint system, you have an estimate for that And so you would use that right here. If you happen to use it at the previous time step, I guess that would be okay. It would still converge, but it wouldn't converge as quickly. So use your most recent estimates. Square that thing out and divide by those responsibility indices. So just another weighted average of the squared errors. So makes sense. Again, if you're looking at the MLE, this would be 1. If you knew the Z's, that would be 1, and then you would be dividing by the group model size. Some people would subtract off the number of parameters that they've estimated in there as well to come up with the unbiased estimator, but that is the maximizer. So the MLE isn't the n-1 thing or the n-k thing, depending on how many groups you have. So, but it looks like that. So it's very similar to your typical MLE. Your biased estimator of sigma squared, which is a better estimator than your unbiased estimator. We'll go through that on Monday. So there's an example in your book that demonstrates that. So it's a little bit biased, but it's the trade-off in variance makes it work. So this is how you do everything. What would happen if you wanted to get rid of that and you wanted sigma? The way that I've written everything down here is I've got sigma squareds here and I've got a sigma here. So I've treated the parameter differently in 2 different places. What would I do if I wanted this? Can I just do this? Is that still the MLE? Anybody want to? Yeah. So it turns out it's true. So some people are like, maybe not. You know, it sounds like I might be tricking you. It turns out for MLEs, this is true. You can transform them directly and it preserves the maximum. So we'll go through that proof in a second. But that's called invariance of the MLE, is that I can just transform it directly. So that's a property that maximums have. I should say it's not a property of an MLE. It's a property of maximizing something that's not a random variable. So that's true for any function where it's not a random variable. You can always do that. So if they didn't teach you that in calculus class, it's always true for maximizing functions as long as it's not a random variable. So meaning there's no Jacobian term I need to deal with. It changes the stretch over the space. Okay. So these are the things that you're going to be implementing in your homework. You'll have higher dimensional versions of this. This estimator will look exactly the same. Right here for the high dimensional analog, this will just be a vector. But it'll look just like this. That will be a vector, this will be a vector for your high dimensional cases. This will look a little bit different. This will just turn into xi minus mu k to whatever that index is, transpose multiplied by itself again. So it'll look like an inner, or sorry, let me say that again. It ends up looking like an outer product. This right here. This is going to be a matrix, so this should be an outer product. So this whole thing will change to xi minus mu k t plus 1 times xi minus mu k t plus 1 transposed. This is a matrix. So, and that's the only thing that changes there. So that's the higher dimensional analog. And when you go and you take your derivatives over cap sigma, your covariance matrix, and you do everything. And if you do everything on the precision scale, the inverse of it, it turns out the same because you can just invert that estimate because they're MLEs and they're invariant transforms. But you'll just change that out, and that's what's written in your homework. So the only thing that's not written out explicitly in your homework is this step right here, these model probabilities. So that's the first line of the thing that you'll need to do. You'll need to do this for each I and each k. So you'll have a loop running, and you can update all of these. You don't need to do it for every k, you only need to do it for k minus 1 things because of everything adds up to 1. I don't know what's actually faster on a computer. Doing the subtraction by 1, that's probably faster, but computing this one more time isn't that big. So you could do it for all I and K. If you wanted to, you could save a very minor amount of time by using the constraint that everything adds up to. Sometimes that stuff helps you a lot, sometimes it only helps you a little. You can kind of tell, it's not going to help you too much. Okay, any questions about all that? That's EM. So here's what's going to happen. So all you're going to have to do in this is just run a for loop over this stuff. For T goes from 1 to cap T. Now, of course, you're going to have to update these at every step inside of these for loops. So you're going to have an inner for loop right there, updating all these model probabilities. But once you have those, you're just going to be updating those and updating those over and over and over again. So it's just an iterative process. You initialize it somewhere, probably initialize your original mu's and pi's. If you have an initialization for your original mu's and pi's or mu's and sigmas, then you can compute all of these and compute all of your pi's. You compute all of your pi's, and then you're updating those things. Then you come back here, you update all of your pi's, you do those again. And that's it. So we're not taking the expectation at every step because we already have Q and we know how to maximize it. So it's pretty easy code to write. Let me show you a version of this code. This is a simpler version than what you're going to do in your homework. I'm going to assume in this version of the code that I know what the sigmas are and they're the same. So what my code is going to do is it's going to estimate all of those and just do the mu. So, and update those. So your investigation will be just a little bit deeper than this one, and you'll be doing this in ID. Some of you might come back and say, you didn't say which dimensionality to check, you didn't say which values of mu and sigma to simulate from. You are allowed to choose those. So you should pick values that you think are worth demonstrating how well the algorithm works. What I usually like to do is show off cases where my algo works very well, and cases where the algo doesn't really work well. You can kind of imagine if the modes get pushed real close to each other, it's harder and harder to identify everything. So if the modes are overlapping each other a lot, it's hard to identify stuff. So when the modes are very far apart from each other, it's very easy to identify those modes. And you can kind of imagine that just by visualizing the modes. You know, if you were to do this with your eye in one dimension, you could probably do it very well if the modes are very far apart from each other. Just draw a line between them. So if the modes are overlapping, you might not know how to do that. Let's see if we can look at a couple cases like that. Christina, could you do us the favor? Thank you. We've got some EM stuff, EM example. Here's my example right here. I'm not going to give you this code, so just because you're going to be coding something out that's super similar to it, but there's nothing fancy in any of this. If you get really stuck, I can show you again, but you'll have a video to scroll through it. So this is the mixture model that I'm going to be sampling from, so 2 components, so a little bit simpler than what you're going to be doing. So I've got one key, I've got mu1 and mu2, and the variances I'm just going to lock down immediately. Make everything simpler. I input what my modes are so that I can sample from everything, and I input a true key. My variance is locked down to mu1. I'll sample 1,000 data points from this. So you can vary all of that stuff. What you'll notice is if you move into very high dimensions, you need more data to estimate everything in high dimensions. And that kind of makes sense. So this problem of the modes being unidentified or harder to identify as they move closer to each other, that closeness is relative to variance and also relative to the sparsity of the space. So you can learn about the curse of dimensionality. It just means the space is empty. It's harder to estimate things. So what I'm going to do is I'm just going to sample from everything. So this is just sampling from my mixture model. Same stuff that we did in the bootstrap code. Very similar. I've got a histogram. I'll plot it for you. And then I'm going to run EM. So here's my inner for loops that update all of the pi's. That's my PP here. And then my P itself is just the mean of those. So I don't actually use this. I just compute it just for the heck of it. So, and then I do all of my updates right here. So I've got those PPs. Now this is that weighted average right here. So that's all I'm doing for computing the mu. And that's the end of everything. And I'll just print out everything to you so you can see it. So I do print out the P to you so that you can actually just see what it's converging to. Hopefully it's converging to something like the parameters that generated the data. So that pi k update at t plus 1 is estimating this thing. So let's just run this. It's all my stuff. You can kind of see the updates happening. So the mu's are converging to 10 and 2. And my model probabilities are something like the truth. So it seems to be doing okay. So that looks like about 0.7 and 0.3 with some stochasticity to it. Of course, it's not perfect, but as I get more and more data, I'll get better and better and better. I probably should check for a local optima, but everything worked out really good. I could change everything and rerun everything again and push these modes closer to each other. So let's make that 9 and 10 and see how well this does. EM algorithm. It's shockingly decent. You can't even do this. Like if you try to do this with your eyeball, you would be like, I cannot see the breakpoint. The algorithm does a pretty good job. Something around 9, something around 10, and it has those model probabilities approximately right. They're not quite right. It's very hard to distinguish things in the data. So this middle ground. And so the algorithm is having a hard time distinguishing things, but it gives you decent estimators. It's amazing that it can actually do this. So, because if I glanced at this, I wouldn't be able to tell with my eyeball at all. So the algorithm is probably better than you think that it is. It's better than your eyeball, even in one dimension. So that's kind of cool. Let me just go back to another case real quick and just go back and make these strongly identifiable. So I'll say the terminology that people use when it's hard to identify things and it becomes, the modes get closer, they use the term weakly identifiable. So there's some identifiability there. If I push those modes completely on top of each other, you couldn't distinguish anything. It would be the same as using a one-component model. And those P's themselves, the model probabilities, it wouldn't matter what they are. So in those cases, we would say those are unidentifiable. So you can't identify them. So I'm going to make a point real quickly for a Bernoulli model where you're just sampling one data point. If you have a mixture of Bernoullis, you cannot identify that Bernoulli. So it turns out a one Bernoulli model is the only thing you can really estimate with a mixture of the model parameters. I'll let you think about that a little bit. So if you ran an EM on a Bernoulli mixture model, it would never converge to it. It would converge to something that's sensible, but the answer would be all over the place. There's an infinite number of combinations that you can come up with. So some mixtures are not identifiable, and if you run EM on it, you seem a little silly. So sometimes I ask questions like that on QE. So people go through a lot of work, and it's really a one-sentence thing. These are unidentifiable, and this is the best you could do. You should not run EM. So that Bernoulli problem sometimes I ask. It's a 1 or 2 point sort of thing just to see if you're paying attention. Are you just doing a bunch of stuff because you can, or because you should? So let me just rerun this again. EM algorithm runs really good for this. So this is 10 and 2. Again, and the model probabilities seem to be converging to the right thing. That's good. Remember, this is 10 and 2, 0.7 and 0.3. Let's rerun it again. Nice, these just flipped. Now this is 2 and 10. The model probabilities flipped. The algorithm has no ability to distinguish which bucket I'm putting things in. All it knows is buckets. So this is called label switching. When that happens, your code does not know anything about the labels. And it will arbitrarily flip these things around. So sometimes when people are running big simulation studies, they need to control for the label switching problem. And they sometimes will order the model probabilities, that they'll let P1 be less than P2 be less than P3, so that you're always throwing the smallest thing over the first bucket. And that's as easy as just taking these and reordering them at the end of the day. So that's your correction for label switching, is just reorder according to these model probabilities at the end of the day, and they should align with the correct nodes. So I've heard people say I have some theoretical work that I'm working on to fix the label switching problem. That's as good as you can do. Just reorder everything according to this so that you're comparing apples to apples. So you might be running a simulation study seeing if you hit 2 in the first component every single time, and it's label switching and you're comparing 10 to 2 and 2 to 10, and your MSE seems incredibly high. So you've just made an evaluation error. So just be aware of that your code doesn't have the ability to distinguish label switching unless you encode it. That's it. Any questions about all of that? Okay, let's do invariance of the MLE. It's a one-line proof. I think you only get this stuff once you code it. Run through the math yourself. It's not something that I think you can fully understand massively. So enjoy the assignment. Christina? Okay. Invariance of the MLE. Basically, it says I can just transform my MLEs and I still get the MLE. So let me just make a statement about this. I remember the proof confusing me in the book ever so slightly, and so I'll tell you the part that I was confused about some number of years ago in graduate school. We used the same book, so exactly the same book. No updates. It's a good one. The only problem with Cassell-Emberger is it covers so many different branches and says so many different things, and the level goes from super easy to super hard. I consider that a good thing, but I can understand at first read it can be a challenging book. Okay, invariance of the MLE. This says this, that if you have this, theta hat MLE, I'm just going to call it theta hat because we're only talking about MLEs here. This thing is the R maximizer of theta log theta given x. They replace this maximum with the supremum operator. It just means sometimes you can't obtain that actual value of theta, but you can get epsilon close to it. So in our class, we're going to assume that we're going to obtain everything. And so we won't do the supremum thing. So just change out your supremums for maximums. And if you get into a measure theory class, change out your maximums for supremums. So just to cover all cases. So my proof will just look a little different there because it doesn't matter. Okay, so if I have that, but I want to reparameterize, and I didn't want to think about theta, but instead I wanted to think about a function of theta. And I'm going to call that thing eta right here. So this is just a transform. So when I wanted to not think about theta, but I wanted to think about eta. So an example of this would be, sometimes some people like to think about sigma squared in a normal model, and I like to think about 1 over sigma squared. It's just as arbitrary. So the reason I like to do it is because I like gamma distributions. That's the only reason I like thinking about this. So sometimes it makes your calculations a little bit easy, but again, it's totally arbitrary. Some people have tried to convince me that that's the natural thing to think about. You're naturally indoctrinated. There is nothing more natural about that than that. So, and they're one-to-one with each other. So you're just used to thinking about sigma squared. So this would be a transformation of this. So this might be tau sigma squared. So I want to just change the way I think about parameters in my model. I would agree that 1 over mu in a normal model probably isn't the most natural thing to think about. So means I can accept it, but higher order stuff, and just to express the point a little bit more, naturally you don't think about kurtosis or anything like that, or third moments or skewness and stuff like that. So, okay. So you want to transform that. It's very easy. So if you wanted eta hat, this is going to be the MLE for eta. This is just going to be tau eta hat, or that's that. So I just plug that thing straight in. It couldn't be any easier. So sometimes taking maximums over functions of things can be easier. You know, and reparameterizing things can be easier, and then doing the transform at the end. That's true for transformations of variables too. So there's different ways to do it where you can transform things right at the end. Bless you. Let's just look at a quick proof. This is the one, this is the proof in the book. It's a one-sentence proof. My proof is going to assume that everything is one-to-one with each other. This result is true regardless if tau is one-to-one. This is true all the time. Always true. I will address the more general proof next time in class, just ever so quickly. So it is a redefinition of the maximum, what you would actually do, and I'll say what that proof is about. So we'll spend about 5 minutes on that next time. But this is going to assume tau is one-to-one. So tau inverse exists. Again, this doesn't matter for the result. This is true regardless if it's one-to-one. I'll probably ask you to do this proof on the midterm in the one-to-one case. And if you want to embellish it with the non-one-to-one version, I'll be impressed minorly, and I'll give you nothing for it. So you can just think about this case over the weekend if you'd like. So this is just going to say the maximum. I'm just going to deal with the maximum problem, although you're going to get the arg maximizer. I'll write everything just in terms of maximums. They're akin to each other. If I can maximize something, I can find the argument that maximizes it. This is the part that changes just ever so slightly in the non-one-to-one case. The book does this. Say I've got my likelihood function parameterized in terms of my transform variable. This is the part I didn't like. They threw a star on top of the likelihood. This is the first time in the book that they distinguish the notation between, you know, what I usually call the F's, and I'm like, the F's are different. It's a different random variable. It is not the same function. We should express those functions as different. This, unfortunately, is exactly the same likelihood. This is the exact same function right here as it would be parameterized under theta. That's the part I don't like. It was unnecessary to do this. In the one place that they do it in the book is the only place it doesn't matter. So they end up saying that this is going to be the maximum. They do distinguish this right here in the book. They're going to say this is the maximum of the likelihood. This is theta's likelihood. And they say that the definition of this is just going to be tau inverse theta. Or, tau inverse eta. Right here, where this is theta's likelihood. They're exactly the same thing. I'll go through an example next time to demonstrate these are exactly the same things. You don't transform the function. There's no Jacobian when you transform likelihoods. It's the same function and you just reparameterize it. So that's the same thing right here. I guess this is the part that they make a big deal that those L's really are the same and I reparameterize it. Wherever I see a theta, I interchange it with a tau inverse eta and I can write that thing down directly. So if I can write down sigma squared, I can write down phi in the model. We'll go through an example next time. So the way I like to think about this is I can either search through the maximum of this function space by turning eta. What I mean by turning eta is I mean I'm just shifting it, I'm moving it around. So it's a nod. Or I can take a function of eta and I can move that function around and we call that theta. And I can find the maximum either way. It doesn't make any difference. I like to think about this as like in terms of gears in a car or a bicycle, if you know how those work. I do know how they work. So one thing I can turn real fast and do something and turn the wheel over a certain amount of times, or I can switch the gear and pedal slower and turn the wheel around exactly the same amount of times. I think about this as the same thing. I can either budge eta or I can budge theta, and I'm budging them at different rates. Is all that you're really doing, but you're still moving through this function space. So this is the same thing as max over theta of the likelihood parameterized in terms of theta. I think an example would help us to see this, but this is the proof right here that says they're the same. You can interchange all the arc maximums to everything. They have one more line in here where they say this is eta hat right here, and this is theta hat. It seems like everything's so obvious in that proof. What does it really mean? Let's come back, glance at an example next time. Show just very quickly the non-one-to-one version of this proof. If you want to see it, it is in the book as well, so you can glance at that. And then I'm going to just switch into evaluating estimators, and I'm going to tell you about the MSE decomposition bias squared plus variance. So most of you know about that. I'll talk about other operators, other evaluators like absolute norms or 0-1 loss functions, and then we'll do yes, no, maybe for the last 15 minutes of the class. We have a midterm on Wednesday. That's it. Enjoy the weekend, you guys. It should